This is going to be a little bit new. I don't think you would have done this in grade 10, so this was probably new to most of us. And again, you'll notice it has a lot to do with notation. And we're going to practice some algebra and some different things like that today too, and on Monday, because we're going to do 2 days of this kind of work. But it's just notation. So some people get confused, like, I don't understand this, I don't understand this. There's not really anything to understand. It's just it's just the way it's being written, and you just have to get used to it. But otherwise, what we're doing today, most of it is not very new to you. You've seen it before, it doesn't look exactly like this. I hope that makes sense. So before we even start, we're going to talk a little bit about functions in general before we get to the notation part. So consider this function, y is equal to 3x. I like functions like this because the relationship is easy to understand. And relations is what functions is all about, the relationship between the x and the y. And graphs are all about relationships, and using graphs and graphing and solving problems with them is all about using relationships to solve problems. So if I think of this relationship and I kind of do like an x, y table, somebody give me an x value. Any number, make it up yourself, 2. And if I put it into this function, I do 3 times x, which is 3 times 2, which is 6. Somebody give me another one. 4. So I do 3 times 4, which is 12. One more. So that's all I can fit. Nora, give me a number. Awesome. Good choice. 3 times 7 is 21. All of the y's are tripled from the x's. 3 times the size. That's the relationship. That's what this equation means. It means you take a number and you triple it to get the other number. One group of numbers is always 3 times the size of the other group of numbers. That's a really simple relationship. And all the relationships, quadratic, the parabolas that you saw last year, like those are all more complex, but it's the same idea. Those equations, those formulas, those graphs are just relationships like this one. This one's simple, 3 times the size. One number is 3 times the size of another number. You pick any 2 numbers where one is 3 times the other, it'll belong in this relationship. 10 and 30 belongs in that relationship. Does that make sense? So it's a relation. Now, something that can be important to think about with relations is there's the ones that we study. There are other relations, but the ones that we study have 2 variables, the x and the y. One number and the other number, and the relationship between them. And one of the variables is the input variable. So notice we were picking values of x, plugging them in, and calculating the y. So one of those is the input variable, and one is the output variable. And every equation, every formula like this, like y equals 3x or any of the other ones, has an input and an output. You put something in, it spits something back out at you. You put something in, it spits something back out at you. Does that make sense? So the input variable, we usually think of that as x, and that's your horizontal axis. And the output variable, we often think about it as y, and that's your vertical. And it always is like that. Input is always like this, output's always like that. And there's another, and that makes sense, right? There's another way we talk about it. We talk about the y value depending on the x value. Because what you get for y depends on what you put in for x. Does that make sense? Depending on what I put in for x, I'll get some y. If I put in a big x, in this case, I'll get a big y. If I put in a small x, I'll get a small y, right? Doesn't that make sense? So we call y the dependent variable and x the independent variable because y depends on x. So I want to ask you a question. Yes, go ahead.
It will never be x equals like 3y.
I mean, you can rearrange a formula to look like that, but we never write formulas like that. We as a standard always write formulas in terms of y. If you wrote it in terms of x, then you would kind of be thinking about it flipped around the other way, and X would depend on Y. And you could do that. Like, you could do whatever you want, right? But it's easier when we do it this kind of the same way all the time and think of it one way and have a standard. Okay, so if I do this, if I do a graph of distance versus time, which one is the dependent variable? Which one is the independent variable? And almost always, time is the independent variable. Because you can't stop time. Time just goes. But how far you travel depends on how long you've traveled. Okay, so distance is the dependent variable, and that's our y variable or our vertical variable. It goes up the side, and time would be independent, right? It's not like more seconds passed because you traveled farther. No. If you're going at a particular speed, you travel farther because more time has passed. Do you see how like it's a one-way idea, one-way dependency? So distance depends on time. And then you could graph, like whatever the graph looks like, I don't know. Over time, your distance increases. I don't know what this graph is about. It's just an example. Okay, let's think of another situation. Can you think of something else that would depend on time? So not distance. Say again? Growth. That's height, which is a type of distance, but very good. Growth. So we could actually call that growth. Or maybe height. Or maybe you weren't thinking growth tall. Maybe you were thinking some other kind of growth. But so absolutely, yeah. Growth of a balloon over time, if it's being blown up. That's great. Anybody else?
Could you do a cost?
Cost over time, what would that be? What would be a real life example of that?
How much you make per hour.
Okay, so earnings per hour, or cost of a plumber, we talked about that yesterday, per hour. So the more time spent, the more it would cost. It's not like it cost more, so because of that, it worked longer. I mean, you might think, well, I'll pay you $100 and you work as much as that would do. Like somebody might think of it that way, but that's still not the way the dependency works, right? And what about something that's not time? Here's one I thought of. Number of items you buy at the store, and again, cost. Right? So if you buy more items, it's going to cost more. Does that make sense? One of the variables is in all of these cases is depending on the other. Now, if anybody did take data management next year, if anybody was planning on doing that, we talked about this earlier. You talk about this a little bit, and sometimes you could graph things, but one doesn't depend on the other. They're actually totally independent variables from each other, but that's not what we're talking about. So there is a whole branch of mathematics, statistics, and data management where they talk about dependency of variables. Something like, there's famous examples, but I'm just going to try to think of one. That would be two things that have gone up over time but have nothing to do with each other. I don't know, can you think of anything? One that's sort of famous is sort of like is number of computers versus like how hot our planet is getting or something like that. Like the number of computers isn't actually making the planet hotter, but the planet's getting hotter and we're getting more computers. So those two things happen to be happening at the same time. Maybe both of them are a little bit because there's more people around, but one's not causing the other. Anyway, okay, here we go. So it turns out, so we have been writing functions always like this. Y equals 3x with y's and x's. Turns out there's another really useful way of writing functions. It's just a new notation. It's not different from the x and y notation that we're used to. It's called function notation. The only difference is we can use x's and y's for things that are not functions, like circles, but you would never use function notation for something that isn't a function, almost never. Okay? So that's the only difference. And function notation, if I wanted to rewrite this as a function, I write it like this. It doesn't have to use x. It also doesn't have to use f, but that's generally how we do it. So we replace y with this. And hopefully by the end of today, you'll be convinced a little bit of why this is useful. So one thing, I kind of said it there, but f, in this case, f replaces y as the dependent variable. We're just going to make a couple of notes here, and then we're going to start using it. Yeah? F, it says the same thing as that. F bracket x bracket. One of the nice things about it is we can use all letters. Whoops. So we've got F, G, H. Some are more common than others, but you could use any one you want. Sometimes we use capital letters. Like we would often use D, if we're talking about distance. We often use letters that make sense for the problem we're talking about, or capital H if we're talking about height. So we can use letters that make sense. We do that with this too. Sometimes we use a capital C for cost. Okay. And just so you know, the value of f, what it means is the value of f at the value of x. So we say f at x, or sometimes we say f of x. F at x or f of x. These, and we kind of, some people kind of like slur it all together and it sounds like f at x. But that's what that means. We're talking function notation. Okay? Does that make sense? On the back of your page, once you get that copied down, you'll find some examples of exactly how we use this. So example 1, evaluate the function f at x equals 4x plus 1. Some people hate new notation because they're like, it was fine the way it was. Why do you have to change it? Now I have to learn a new way of writing the same thing. What in the heck? Like, why are you doing this? But there's reasons why we do it. We can talk about different functions at the same time. Function f, function g, function h. We can give them different names. It's got a really nice way of like saying, okay, so this is my function, f at x equals 4x plus 1. What's f at 1? What's f at negative 2? What's f at a half? So it's got a nice, simple way of writing those things. Okay? And so that's why we like this. And we're one of the reasons why we like it. And here we go, f at 1. You've done this before. You did this back in grade 9. You probably did this in elementary school. All we do is replace the x. You don't have to do the open bracket 1. We're going to do it once. With the number in there. So whatever is here goes in there. And then now it's BEDMAS. 4 times 1, 4. 4 plus 1, 5. So for this function, f at 1 is 5. What do you think? Fine with this so far? Not bothered, not worried? Good. Let's try another one. So I'm replacing the x with the number in the brackets. So in this case it's -2, so make sure the -2, the whole thing goes in brackets. And this question just wants us to evaluate it, so all we do 4 times -2 is -8. Plus 1 is -7. And a little bit of practice with fractions. If you still struggle with fractions, I would encourage you to start thinking about what it really means. 4 times a half is a half of 4. That's what it means. I don't need fraction rules to solve that question. I just need to know what half of 4 is. Brooke, what's half of 4? 2, right? So 4 times a half is 2. Maybe that's an easy one, but think about it that way. Okay? We got a new function h at x. Given the function h at x equals 2x squared minus 3x plus 1, so this one's a quadratic. Find h at 5. So what do? I do 2x squared minus 3x plus 1. All my brackets are empty. Take the 5 and put them in for every x. Not just the first one, not just the second one, every x. And notice that the squared is outside the brackets. That's really important. And then BEDMAS. Go ahead and solve it. And why don't you try the next one? The one thing that's really useful to think about and start to sort of make sure that you're getting it correct is when you have an x squared, and you're putting in your brackets, the squared is outside the brackets. That's going to make a difference in some questions. Some it won't and some it will. But it should always be like that. And you should get in the habit of doing that and sort of like be mindful that it should look like that. Think about it when you're doing it. This question is one where it highlights why it's important to have the 2 outside the brackets. So when I put the -1s inside, and we remember that -1 squared and -1 squared are not the same thing. -1 all squared is -1 times -1, which is +1. And this is -1 times 1, which is -1. So it's the difference of a negative and a positive, which makes a big difference. Do you owe money or does somebody owe you money? That seems like a big deal to me. So this is -1 all squared. So this is 2 times 1. Whoops, not equals. Exponents first, right? BEDMAS, do exponents first. Then multiply. Negative 3 times negative 1 is plus 3 plus 1. And you get 2 plus 3 plus 1. I saw a lot of people have 6, so that's awesome. And what about with a decimal? Well, it's the same thing. So 2 bracket squared minus 3 bracket plus 1, and inside the bracket, whoops, not 0.01, sorry, 0.1, 0.1, and get your calculator out to do this stuff. Not too worried about the BEDMAS steps and showing your work at this stage. You could type it into a calculator, but even like you should be able to do it accurately without a calculator. But what you might not know what 0.1 squared is, because we don't do a lot of squaring or multiplying decimals. So what is it? Anybody? 0.01 minus 0.3 plus 1, which is 0.02 minus 0.3 plus 1. And that, again, on your calculator, like this, that's not hard to do in your head, but we just don't do a lot of adding decimals, so we're not used to it. Everybody okay? A few more examples here. A couple more. Honestly, the only thing about function notation is just getting used. This is what I said, getting used to the notation, getting used to what it means, how we write it, that kind of thing, so that we're going to use it throughout the whole course and you just are familiar with it. This one's a little bit different. If d at t, so this one looks to me like it's like distance over time. This would be a common way that we would write distance over time. This question isn't about anything, so I don't know, but it's just an example of what it might look like. So we don't know, whoops, that shouldn't be an x, that should be a t, right? So the variable should match, and that should be a t. Oh boy, okay. So you can use any variable instead of x, and you can use any variable instead of f. Capitals, little letters sometimes we use. So d at t. So this says find the value of t when you're given d at t. So this is like the opposite of if you're given y, you find x. This is the same thing. So if d at t is 7, that means 7, you don't need the therefores, I'm just doing it. That's telling us that 7 equals 3t minus 2. It's giving us the value of the function and asking us to solve for the independent variable. So I move the 2 over, add 2 to both sides. Divide both sides by 3. And I found t equals 3. Try the next one. So I'm going to add 2 to both sides. And negative 8 plus 2 is negative 6. Divide both sides by 3. And I get t equals negative 2. And then the last one, 3t minus 2. Add 2 to both sides. 7 equals 3t. And t equals 7 over 3. Divide both sides by 3. Got a fraction. Fine. Last example. This is just here because I think there's a question like this in the practice tonight. List the ordered pairs of the function g at x equal to 1/2 x minus 3 when the domain is this. So we'll do a little bit of this throughout the course. This is one of the ways we use domain, is we use it like this. We say, if the domain is this, then what are the possible ordered pairs, or then what is the range? Like, this is kind of one of the ways that we talk about domain and range. So what is this actually asking us? It's saying it wants us to list the ordered pairs. So we're going to think about it as like, it's not x, y, because it's not y, it's g, but it's the same idea. We're going to list the ordered pairs x comma g for these 4 values of x. That's all this is saying. So we're going to do g at -2. We'll start with that. G at -2 equals 1/2 times -2 minus 3. So half of -2 is -1. And that's -4. What was the next one? G at 0. Go ahead and find the other 3. So I got -3, -2.5 or 5/2, 5/2, and -1. And it says list the ordered pairs. So our ordered pairs are, if you want to watch, you can watch -2 and -4, because when I put in -2, I got out -4. So my input was -2, my output was -4. So it still creates an ordered pair. 0 and -3, 1 and -5/2, and 4 and -1. And if I wanted to do my range for some reason, my range is -4, -3, -5/2, -1. Yeah?
When x is 1, I got -2.5, so it's 0.5 minus 3.
What's 5 divided by 2? On your calculator, do 5 divided by 2. It's 2.5, so it's the same thing.
Okay.
Yeah. And that would be fine. I think I've talked about this. You know, I will, now that I look at it, I missed part of that. I will sometimes use fractions, like if you did it with a decimal like that, you're right. That's how it would, your calculator would give you the decimal answer. And I converted that back to a fraction, and I'll do that sometimes. But as long as it's a terminating decimal like 2.5, totally fine with me. Okay, so this page is from the same section as we were working on yesterday. So you can go to the post from yesterday and go to 179, questions 6 to 12 and 18. If there are any questions about the homework from yesterday, I'm happy to, we got lots of time, happy to work on them. I'm going to hand back tests and that kind of stuff. If you have any questions on the tests or anything like that, you can talk that over too.